unmute. That works. Okay, hello. I'm too loud. So I'm going to talk about face swap, step-by-step instruction how to do it. It's going to be probably crafted work without any magic like neural networks, convolution, and so on. So actually, convolution will be there, but without magic. I also need that. Okay, works. So first of all, I need to know if in this room there's a person who didn't even think about face detection, face swapping, landmarks detection, and just came here because the topic sounds like it's lightweight for the late conference day. So is such a person here? Like, of little experience? Okay, so maybe I will randomly choose you. I know you work here, but you're gonna help me. So imagine that you have two images, not a video. The presentation is about video, but let's imagine you have images. And you want to crop out face from one picture and paste it into another. You have Photoshop, for example. And can you explain what steps can you take to do that? You actually have the microphone already. That's awesome. So let's try. Okay,
so I will detect features like
no detection. You have your mouse. You have Photoshop. You
only do mouse. Okay.
Yeah. No
sure.
Automation. You do it by your hand.
I know, but detection sounds more professional.
Okay. Yeah. Okay. So step by step. Let's say 3 steps. I think that's enough.
Only face, no hair.
No, just face.
Okay. So I would provide the frame of the face, but I would also mark some features like nose, eyes, and lips. I would stretch. I don't have to do that because I can stretch that face to fit to another one. To stretch in that way, it might look very strange, but only one step would be enough. Just to mark the face and then stretch it to fit to another.
Okay, so that's some idea. So you have 2 pictures, face. You get the face from the first one. Yeah. Let's say you paste it on the another and just stretch it a little bit so that it fits. Yeah. Let's say, okay, that sounds good, and that's basically a principle. This is how you do it. And we have different methods, so for achieving different results, you can do as much as you said, or we said together. You can do something more, and we will do something more. But the principle is the same for everything. So let's start with the first slide. I will introduce myself right now. I'm Sylwek Brzęczkowski. I'm a husband, I'm a father, and I'm a Python developer at TrustAmp, in that order, usually. And just an information, after this talk, I need to just go and run for my train. So if you have any questions that I won't answer in the Q&A session, send me an email. My GitHub, my LinkedIn, that's it. And also about TrustAmp. TrustAmp is a US-based startup in Atlanta, Georgia. We're working on know your customer solutions for banking industry, mostly. And we work tightly with Warsaw software house 10Clouds, which are just across the river. Where's the river? Somewhere there. And I actually came from 10Clouds, then we were transferred directly to TrustAmp, and we still have some projects in 10Clouds. So if you want to work for TrustAmp or 10Clouds, then I can answer the questions if you want. Let's start with the agenda. So we're going to talk about, one note. I thought I have 40 minutes, but I have 25. So I think I'm going to speed up a little bit. So we have face detection, facial landmarks detection, finding face border, that's important, approximating nonlinear operations, finding triangles for image transformation from the previous point, blending images together, stabilization, video stabilization. Okay. So let's talk about the goal. So you more or less know what are the mechanics behind apps like Snapchat. You know how to tackle the problem of face swap. You know that most of the heavy lifting is already implemented in dleep or OpenCV. With one exception, I'm going to talk about this. And you know why face swapping fails so often. So meta info, just about the talk. So I don't see that because I have a timer. I will go here. So the ideas for solutions comes from mainly from learnopencv.com and imagesearch.com blogs. If you're interested in the topic, I encourage you to go there because there are people that are passionate about that and they create awesome stuff on this blog. So I recommend you to visit it. The second one is examples are written with OpenCV, dleep, and NumPy, of course, in Python. Save questions for the Q&A session unless you notice real not true, for example. And remember the slide name. That's gonna speed up a bit because I said I thought we have 40 minutes. We'll use pictures of the following stars in the examples. So that's Clint Eastwood, Jamie Foxx, Pamela Anderson, and Krzysztof Krawczyk. So first of all, face detection, histogram of oriented gradients. That's one of the methods. We have other like Haar cascades and probably even thousands more methods of detection face. So how histogram of oriented gradient works? In a nutshell, all you have to know, I don't want to go into details in this presentation. You just need to know that feature descriptor. That means we have some image, and out of this image we produce feature vector. And then this feature vector is an input to some classifier, for example, SVM. And that's it. So once we have that classifier trained, we have, let's say that's a picture of people, my audience, and I need to find all the faces in this picture. So what I do is I look for these faces using small, in this example, square patches, and I'm looking for it just moving step by step when the steps are pretty small. And I'm also using a smaller scale. I'm using all of it. And I'm trying to find, and all of this, of course, I forgot to say that these small patches are producing HOG or histogram-oriented gradients feature vectors that are then passed to the classifier. Classifier returns some result, and then the face is detected where the result was the highest. Simple as it. That is it. So how to implement that in Python and dleep? Maybe I will stand here. Okay, so how to implement that? That's pretty simple. Import dleep, import OpenCV, create. Maybe I will show here. With the mouse, you just import the stuff that we need. We create get frontal face detector object. We load an image and we use detector to. Okay, I need you here right now. Okay, so we load the images, and the return is rectangles. There might be known rectangles, one rectangle, more rectangles. That many rectangles that are faces in the picture. So, could you? So this is how it works. I hope it will work. So that's the. Oh, actually, I think I can use it right here. Okay, this is how it works. And now, let's assume that we are use simple copy-paste image Pamela, not rectangle. Okay. One more time. Doesn't look good. Okay, let's go further. Facial landmark detection. So We also use dleep in this case. Dleep returns, for a given image, it returns 68 facial landmarks. And it's important to understand that every point has its own identifier. It's unique for the whole face. It's important to understand because if you detect landmarks on my face and I will try on your face, you have the same number, for example, in the left corner of the right eye, which is 43, I guess. So we will have the same identifiers, and this is pretty important to understand. Briefly, how it works. So dleep implementation uses 1 millisecond phase alignment, paper. In a nutshell, what is it called? Phase alignment, not phase detection. So in fact, it's a phase alignment because in the first iteration of the algorithm, as you can see, T0, we have some general facial points on the face. And then after each iteration, T equals 10, we have it's so close to the ground truth that we can stop iterating further. And that means this is why we call it phase alignment, not detection. We align general face to the real shape of in the image, right? And this is how to implement it. It's pretty straightforward. We just add this predictor. We load shape predictor 68 face landmark model. I think the size is around 100 megabytes. This is why it takes so long to load the program. We detect faces and we pick the biggest face. Just to simplify, you can get first face, for example, if you want. I'm thinking the biggest, and you pass it to the predictor with an image and the rectangle in which the face was detected. And the results is the 68 landmarks that we saw. Oh yeah, and how it works. Okay. Next thing that we need is to find the border of the face, and we use convex hull to do it. What's convex hull? So convex hull is for a given set of points. Convex hull is a subset of these points, such subset that the rest of the points is inside this subset, just like on the picture. And some may ask, what's the difference between convex hull and contour, and that's the difference. Green is contour and red is convex hull. So the difference is that it's convex. That's why. And it's pretty simple to implement too. You pass the landmarks that we detected. We need to change the structure a bit. Don't worry about that. And we pass it to the convex hull function with return points to false. And that means that I don't get the location of the points in return. I'm getting the indexes that we are talking about in our faces. That's pretty important stuff to understand. Oh, yeah. So how it works? So my face border will be in blue. Actually, my mask, I would say. Yeah, so getting pretty close to see some results. And yeah, the next thing, approximating nonlinear operations with linear ones. First of all, what's linear operation? Affine transformation, for example. So in a nutshell, that means when you have a line and you do the transformation, after the transformation, this line is still a line. Or if you have parallel lines, after transformation, they are two. So that's an example on the grid, and that's an example in real life. I just shared it a bit, like skewed in GIMP. So this is how it looks. And what's nonlinear transform? It's the opposite. So the line, it's not the line anymore, it's curve. And that's basically how you need to do this so-called stretching that you said about, right? So the face is not flat, as Pamela was on my face in the first example, but it's rather fit better to my face shape, okay? And that's an example. That's a fish eye effect. I think this is how it's called. And why we are talking about this? Because that's pretty common in computer graphics, that we approximate complex objects with triangles. That's pretty common. And we have an example of some complicated mountains shape, and it's approximated perfectly with triangles. Unfortunately, because it's so popular, it doesn't have its own implementation in OpenCV. So you have to create your own one, and I'm gonna skip this. I just want to say, I just want to say that there's Satya Malik, the guy from learnopencv.com, and he implemented that, so you can just go there and see. Basically, that means you cannot get one triangle and transform it into another. You have to do it with the whole picture. So that's the whole, you have to play with this cropping, this rectangular shapes, then you have to use the mask to only apply it for the triangle, not the whole picture, and so on and so on. So basically you need to implement it by itself or use the Satya Malik's implementation. So this is how it works with, maybe one example how it, what I mean by transforming triangle. So that's a simple picture of 10 clouds, like from forever years ago, and there's a green triangle, and we're going to transform it into another triangle, this triangle. So this is not a random triangle. Please pay attention to the circle here. So it's not looking like a circle right now, maybe more like ellipses, I don't know. So basically that's the idea behind warping triangles. And that's how the example works right now. Okay, so we need to find this triangle first. So one of the methods, I think that there are more, but one of the methods to do it, it's the Lune triangulation. And what does it mean? It's just the Lune triangulation just subdivide the space or the surface into triangles in such way that if you look at any triangle on the image, like, for example, this one, and you look at the circle around it, there is no other point that it's inside this circle, right? And this is one of the methods to how to divide the space, and this is how to implement that. So hull is my face border. As you remember, I also added face points so you can see my teeth. And then we just create a subdiv to the object. We insert all these points that I created or detected, and then I get triangles. Just get triangles list, and I have these triangles. Okay, how it works? So it's worth to say that I do that triangulation only once, on the first frame. Later, I use the same triangles for every frame. That's important. Okay, so a little wrap up to make sure that you understand. So, taking some triangles, and taking some points, and then we have some transformations. So the first step is to get some points. In my case, is face border. Add mouse points, the specific indexes that I added manually. Then find triangle, the Lune triangulation for the first image. Find corresponding triangles on the second image, corresponding to the same as on the first image. Transform every triangle from the first image to the second image. And this is how it works in examples. That's my face with points on it. That's convex hull, that's triangulation for my face. That's the second picture with points. That's the same triangulation. And this is what I'm talking about when I say that I transform the same triangle. Right? And that gives us this more or less 3D effect. Okay. So as you can see on the example, we have different color of the skin. There is also a way to fix it. Okay, so let's try to fix it. That's also a complicated idea, so I'll just say in a nutshell how it works. So there is a term called Poisson image editing. That's a paper for that. There's a link below. So the basic idea is that you don't copy the intensities or the values of the pixels. You copy the gradients. It sounds simple. It's much more complicated because it includes some calculus, as you can see in the equation. But let's do not talk about it. The simple idea is to copy gradients instead of intensities. And this is an example. I just pick a random picture from the internet with tattoo, and I need to create a mask for it. So I'm gonna take this region for my mask, and this is how the mask looks. And I'm gonna paste it on my face in random places. Oops. So that's my face with some random tattoo from the internet. As you can see, it's not perfect. Maybe when I work harder with the mask, it will look better, but I didn't have time yesterday. And as you can see on my left cheek, it looks quite awesome. And on my left shoulder, it's also awesome. On the wall, it's worse, but as you can see right now, maybe after the code example, it's quite good. So this is how to implement that. So there's 3 lines about creating masks. So this is how you create a mask, never mind. The most important thing to know is that to use seamless cloning in OpenCV, you need to have source, destination, source image, destination image, mask, center, which is basically the place where you want to paste the cloned area, and you have to pass the method that you use for cloning. So there are 2 methods: it's mixed clone and it's normal cloning. In this example, I use mixed clone. So that's mixed clone. I think normal cloning is not much different. So let's take a look how it looks like. I'm gonna use Jamie Foxx because that's pretty interesting, because the color is different really. Let's try with somebody else, for example, Krzysztof Krawczyk. Better, isn't it? Take a closer look. It is shaky, right? So there is a problem we want to fix. But let's switch to the first example. The second actually. Okay, and please take a closer look again. It's also shaky, you're right. So we want to fix it. But I'm showing that example because I need to tell you that that's the problem with the face landmarks estimation, not with the algorithms that I use later. That's the problem already here. And that's because every detection is based on the single image. We don't have information about the previous frames. And to fix it, we actually have to get this information somehow and use it. So that's what I'm going to present right now. Stabilization. So I recently, so after 2-hour session with my son, convincing him to go to sleep, me and my wife decided to watch some movie and was few days ago, and that was Gangster Squad. And we decided to watch it, even I was pretty hosted. So, never mind. There's a scene, and I decided to put it into this presentation because this guy tells a truth about the optical flow. So he said, don't shoot where it's at, shoot to where it's going. And that's basically all about optical flow. Where a predator, like, I don't know, lion, is chasing its victim, it also uses optical flow. It tries to predict where it's going to be in a second. I don't know, in 2 seconds maybe, based on where is it now and velocity. And that's basically how optical flow works. It tries to predict future position of a point. So that's going to be in a nutshell, of course. So that's the only equation that optical flow has. It's UV, that's the next position of points, and that's some difference between x by the time, and some difference in y's by the time. And there is a problem. It's unsolvable because we have two unknowns, u and v, and we have only one equation. So we need some assumptions to make it work. The first assumption is brightness constancy assumption. It basically means that the same point in every frame has the same brightness, which actually makes sense because more or less that's true. So that's still assumption, so it can be weak. Why not? And that equation says that, but it actually didn't get. We didn't get any new equation, so we have to use some more advanced assumption, which is there are few of them, but we use Lucas-Canade method, which is that the flow is essentially constant in a local neighborhood of the pixel under consideration. In human language, it means that if we have this point, red point, in the center, we assume that all the points around, let's say in this example is 3 on 3 pixels, we assume that all of them have the same optical flow. And thanks to that assumption, we have 9 equations and only 2 unknowns. This is pretty easy to solve. And using this assumption, optical flow works. So this is how to implement that. So as I said, you need to have the previous position of an image, actually the gray version of it for some reason. You need the current frame, you need to have previous points from the previous frame, and you need to have current points from this frame. And based on that, you can have the prediction of the next points. As I said just a second ago, it's a prediction. So we need to combine this information to these points to run smoothly, not just shaking around, just as we saw. So we want to combine this information. So the actual point is a combination of landmark, detected landmark, and the predicted landmark. And I just choose 30% versus 70% because that worked. Okay, let's check how it works. Try with Clint Eastwood. Okay, it's not shaky anymore, but it's laggy right now. So that's the trade-off. But there is a solution for that. I didn't implement that because I didn't have time. You can, for example, make dependent, you can have the 0, 3 and 0, 7 dependent on the velocity of the points. Because as you can show in the example, the faster I'm moving, the more lagging the optical flow is. So you can make it dependent on the velocity, no problem, using some function. Okay, I think that's the summary. So you know the basic steps for the phase swap right now? I hope so. There's the phase detection, landmarks detection, warping triangles, seamless cloning, optical flow, You more or less know how these methods work in general. You have the basic idea if they are hard or not to implement in Python, except for this triangle var. But I promise you it's done by Satya Malik already. Okay, and that's it. Any questions?
Why didn't you just use running average of facial keyboards instead of
So the question was why I just didn't use a simple moving average, actually, right? Yes, you can do it. I didn't because I wanted to show that optical flow, such complicated machinery, is already implemented in OpenCV, and we have that for free. Yes, so the basic idea is to use, for example, let's use the positions of the points from the last 5 frames and use the average of them for the next point, or the weighted average. So the closer you are to the last prediction, like we are in the current frame, so this frame has higher weight, and this frame has a little bit lower, and so on and so on. So yeah, that's also an idea. As I said, we have some principles to make it work, but we have many methods to actually make it work. So that's another one. Any more questions? Because we have -3 seconds for 5. I don't think so. I think that maybe the deep phase have some. It doesn't work that way. Deep phase is different. I'm not talking about porn industry. I'm talking about making, for example, saying words that he didn't say. That's threatening, right? And I think it works better than this. That solution. So yeah, I don't think I know any except for entertainment. Any more questions? I don't see any hands raised. So thank you very much once again. Oh yeah. All the code that I use is on this address. You can just go to my GitHub and there's a phase web repository and all of these examples are there if you're interested how it's implemented. And you can use it on your machine if you want. Thank you.